And happy Monday. Good to see you. Back with section one here. People have been very patient in section one. Thank you. We also have a new TA. We finally got a new TA to replace Joel in section three. And that's Jashurun. You guys in section three will meet him and find out about it. And again, all the TAs have time in the TA room, Zoom spreadsheet, and they're available at almost all hours of the day and into the night. Has everybody seen that TA help room spreadsheet? I know some people have been using it. I posted it under the announcements for our class, so you can find that spreadsheet and get TA help anytime. And don't forget, zoom into my office hours, Tuesdays and Thursdays. It's Tuesdays at 1 and Thursdays at 11. And I'm happy to answer questions there anytime. So yeah, we are finishing up chapter 2 today, acid-base chemistry. Homework 2 then will be due tonight. Remember, it corresponds to each chapter as we finish it there. Quiz 2 is due tomorrow night, so be working on that. And I already warned you a little bit. One of the problems, you have to know something about functional groups, at least identify the general form of them. So chapter 3 coming up, which we haven't started yet, sorry. There's a little bit of that problem, so you might need to read ahead. But I've been mentioning functional groups, and I think you're aware of a lot of them already. You just need to circle a couple of them on quiz 2 there. And then, yeah, chapter 3 on Wednesday. So talking about acid-base chemistry, I like to summarize all the key ideas right here. In fact, I call these corollaries, if you will, of the pKa theory, right? The pKa is minus log of the Ka, which is how strong an acid is. Now that's a direct scale. The bigger the Ka is, the higher it protonates water. And that's kind of a limited definition of the strength of an acid. But the pKa is the inherent ability of that molecule to donate a proton. And that's minus what? The log of the Ka. Okay. And keep in mind, that's an inverse scale now, right? The smaller that pKa number, the stronger that acid. Okay. Sorry about that. That's just the convention. What this means is, the second corollary here, if you have a super strong acid, HA, that means the conjugate base here is super weak, okay? So there's an inverse relationship. And also, if you have a super weak protic acid, what does that mean? You then have a super strong conjugate base. We saw some examples of that. You always form the weaker acid if you're competing, doing a reaction, not involving water. And that's what we're going to start out with here to review a little bit. And then the next thing is, if we go back into water and put these guys into water that can ionize here, 50-50 point, where it's 50% ionized, 50% still protonated, is when you put it in a pH solution that corresponds to its pKa. Okay. Now you can do that with the Henderson-Hasselbalch equation and show that mathematically, or we'll just do it qualitatively. We'll draw out the pH scale and show you at what point a molecule can ionize, okay? And what state it's at then, okay? So we got to remember a little bit about the pH scale. Questions on any of this general stuff so far? Okay, very good. Let's work some problems here. We've got a couple on the board, and we've got the table 2 here, 2.1, I think, right out of your book. A lot of my graphics are right out of the book. All the graphics that you see in class are also posted on Learning Suite. So if they don't show up too well in the videos, or if you want to examine them later, whatever, they're always on Learning Suite also. Let's work these problems here. Let's see what we need to do. We need to identify an acid and a base on each side. And we need to come up with what? The conjugate base and the conjugate acids over here. So what are we talking about? Sodium. Remember, the key there is the metals are always plus and whatever else is minus. So our base here is hydride, which is a hydrogen with its pair of electrons. So those are two different terms I keep using all the time, right? Proton is just H plus, and that's all it is. It's just one proton, and there's no electrons in the 1s orbital, right? So a proton is H plus. But if you have two electrons there, that's hydride. Sodium hydride's a salt, It's a very strong base, okay? So there you go, I'm helping you out, Dave. That must be our acid. So let's draw uh, the curved arrow mechanism there. So remember, the arrow starts at where the electrons begin, and then where they end up, it's grabbing the proton there and pushing those electrons onto the acetylene part there. So what's our conjugate base here? What do I need right here? I need a pair of electrons and what? Is that structure correct as I've drawn it? Somebody had a little dash mark there. What's that? I need a negative charge there, right? So there's our conjugate base. And then what is our conjugate acid here? Well, it's H+. In fact, that's a gas molecule. Sometimes you can see reactions with hydride reagents. You can see the hydrogen gas bubbling out of the solution, okay? Which kind of tells you the thing's working there. What happened to the sodium? Oh, it's just going along for the ride. That's the boring inorganic part, right? We're more interested in the organic part. We need to know what? We need to know the pKa of that molecule there, hydrogen. And it's on the chart there. What's the pK of hydrogen? 35, okay? And what is the pK of the acetylene? 25. So the K for this reaction, we can estimate it. It's the one on the right minus the one on the left, raised to the 10 power. So for this reaction, the estimation for the equilibrium constant is what? 10 to the 10. Is this a favored reaction? Yes, it is. Violently so, I would say. You'd have to carefully control this reaction to get it to go there. Question on this first reaction? Yes?
Yeah. So my question is, how do you know where to draw the arrows? Because I see like the hydrogen's moving and then it becomes like two lone pairs. But then like, I don't understand why one arrow goes one way and the other arrow goes the other way.
Okay. Well, it is somewhat just sort of a convention. We start the arrow where the electrons begin. So you see hydride has a pair of electrons, and it's grabbing H+. Now, keep in mind, a lot of protic acids, we don't see a proton. We don't see H+ sitting there. But that's a proton because these electrons can be pushed toward acetylene, and that pKa is relatively low. It's 25, okay? And we made hydrogen, so you can draw up hydrogen. So, you know, those two electrons right there in the hydrogen molecule came from the hydride to begin with. So, yeah, it's important to identify all those things, but part of it is just convention, you know. The main idea today is, you know, why are certain acids stronger than others? And there are certain factors we need to look at, right? Let's do this one here. So we've got a diketone, and we got hydroxide. So, you know, draw your charges there if you need to. You can already see what? This is your base, and this must be your acid. Now, acid, we've got two hydrogens here. We've got three hydrogens here, three hydrogens here. Where is going to be our proton coming from in this molecule? Is it going to come on the end, the methyls, or in the middle, the methylenes? What do you think? Somebody have an idea? And it ties into a certain factor we're going to be talking about today. Yeah, where do you think? From the middle, someone says. Do people agree with that? Yeah, let's see. Let's just draw one of them there. Let's take hydroxide and grab that proton and leave behind that pair of electrons, right? So let's draw our conjugate base. Look like this. Plus what? Oh, water. Yeah, we know the pK of water. What's that, about 16? 15.7. It's okay to estimate. Oh, and I gave you the pKa there, 10. That's a pretty low pKa. That's pretty acidic for a carbon acid. In fact, we need to talk about why is that so acidic, being a carbon acid, right? So, well, let's estimate the reaction K first. So we have 10 to the 16 minus 10. So yeah, 10 to the 6 power. Very favorable reaction. Hydroxide is a strong enough base to take a proton off this diketone. Now, somebody picked our position for us. We could have pulled a proton off here and had a negative charge out here. What's better about having this negative charge in the middle versus having a negative charge on the end? Yeah. It what? Balances the molecule? You be a little more specific. What factor do you think?
Can you have more resonance?
Ah, resonance. Very good. That's one of the key factors affecting acidity. I like the balance thing. You know, the resulting negative charge can be balanced, you could say. We can resonate up here. So let's draw a double-headed arrow. And what would we have? Negative charge there. Yeah, verify that that's a resonance structure. Is that the only resonance structure? No, it's actually another one. And this is that balance idea, I think. And having it in the middle there, let's just draw, what, a third resonance structure, you could say, right there. If we did deprotonate right here, we'd just have the one resonance structure right there, okay? In fact, the pKa of a methyl ketone like that without any other resonance is about 20. It's a lot less acidic. But if it's right in the middle of two carbonyls, it turns out by resonance, it's much more stabilized, the conjugate base. That's always the key. How stable is this conjugate base? What are the factors that affect that? Okay, let's look first at electronegativity. We'll draw up all these factors here. What affects acidity, and how do we know, where a molecule is going to get ionized? First factor, electronegativity. So let's see. Let's compare the first row. So we got carbon versus a nitrogen, an amine versus an alcohol versus HF. Okay, so right across the second row. Very common compounds, right? Electronegativity wise, we've got electronegativity, and we're talking about the heavy atom. These are all the same. They're all proton donors. In fact, don't be deceived by that. All Bronsted acids are the same thing. They have a hydrogen that can potentially come off as a proton. It's always back to what? The conjugate base, which affects the stability of that bond and the stability of the resulting species, which affects the transition state leading to that product and affects the ground state energy of that product. Okay. So we'll list these factors. First one, electronegativity. What do we have for carbon? 2.5, 3.0 for nitrogen, 3.5 for oxygen, and 4.0 for fluorine, right across there, okay? And let's look at the pKa's. This is minus any other factors, so this is a localized factor here. An alkane, something like methane, it's up there. What's the pKa of methane? 50, okay. Yeah, and what does that mean? That's the highest number. In fact, we have to estimate that number. It's difficult to estimate. Why? Because it's such a super weak acid. Electronegativity, 2.5, okay? And then nitrogen, 38, okay? We have an amide, or an amine, okay? And then water, or alcohols, about 16. And then HF, about 3. So you see them getting progressively what? More acidic. And so the resulting conjugate base is what? Fluoride there. Being highly electronegative, that's going to be more stable, right? It's already pulling on these electrons, right? That's a highly polar covalent bond. And so you can imagine those electrons, the convention pushing the electrons, right, would have fluoride minus to generate the proton, right? And over here, I'll just do carbon. So how stable is that? Well, not very, because what? It has moderate, we say, electronegativity, okay? It's not tugging on those electrons very hard. And so you see, but look at the orders of magnitude here, 50 down to 3, okay? It's an incredible range. I would say electronegativity is the most important factor if you look at the broad range of acids, okay? Very important factor. There's something a little bit crazy here. If you go down the sequence here of the halogen acids, HBr, HCl, and finally HI, you would think, well, iodine, you're going down in the periodic table. That's getting less electronegative. But this is a bigger atom. It's a more polarizable anion. That actually turns out to be the most powerful acid within the series, -9. HBr is -8 pKa, and what's HCl? We learned that last time, -7. So that kind of goes against things, and it has to do with the size of the atom, the weakness of this bond, and the polarizability. It's not directly then electronegativity, because HF is the weakest acid, okay? But that's inorganic stuff. I don't really care about that, but it just rounds out the discussion a little bit there. All right, let's look at another thing here. It's called induction, and it also has to do with electronegativity, but it's not directly on the atom that we're talking about. So here we can talk about comparing different molecules. The pKa of ethanol is 16, okay? A weak acid. It's soluble in water, but it's not going to ionize in water. It's outside of the 0 to 14 range. Alcohols are almost always protonated in water, okay? But let's compare it to this acid. And notice I said acid. This is trifluoroethanol now. There's 3 fluorines there. Now, when we think about this, we always think, well, how stable is the resulting conjugate base? Ethoxide in this case. And in this case, it's trifluoroethoxide. Now, the fluorine isn't directly on the conjugate base where the anion is. But what about the pKa here? Let's have a vote. Maybe we can do it democratically, right? Who says that this number should be higher than 16? Be brave. Who say this number should be lower than 16? Okay. Wow, almost unanimous there. Indeed it is, 12. 4 orders of magnitude more what? Acidic. Which means what? That conjugate base must be somehow stabilized. And we call this a field effect. And what type of field are we talking about? Well, it's an electronic field where inductively we've got some polar covalent bonds here. And notice the direction of all of these, and the 3 together ups the magnitude of the effect. And what? This negative charge here is being delocalized through the field, not by resonance, okay? It's a different thing called an inductive effect, okay? If you can stabilize the negative charge inductively, we're having a proximity or a number of electronegative atoms, and it's seen with halogens typically. You can what? Increase the acidity of a molecule. How about this one? Here we got acetic acid versus trifluoroacetic acid, TFA. We use TFA in the lab all the time. Why? Well, what do you think? It's more acidic or less acidic than acetic acid? More acidic, okay? It's not a resonance effect. pK here is about 5, 4.8 if you want to be exact, okay? Remember, I told you that's one you need to know. The general acidity or pK value of a carboxylic acid, 5. Keep that one locked in your mind, okay? I'm not going to give you a big list of ones to memorize. I'm going to force you to rely on comparing the structures and thinking about these effects, okay? So let's apply the inductive field effect here and see, is this more stabilized? Trifluoroacetate. And what do you predict for the pKa here? Everybody say it's going to be lower. Let's see, how much lower? Yeah, quite a bit lower. It's 2.023, okay? So it's bordering, I would call that a strong acid, okay? It's, near 0, which means it's almost completely ionizing water, forming a hydronium ion. If you add 1 molar, it'll drop the pH down to almost 0, okay? Not as much as HCl or HBr or sulfuric acid, but it's close, okay? For a carboxylic acid, it's certainly much more acidic than this, which we call a weak ionizing acid, okay? So an inductive effect can be very important. It's a proximity issue, and it's a numerical issue. If you have a lot of halogens nearby, the resulting anion of a conjugate base, that can greatly enhance the acidity, okay? Now let's look at another factor. Let's see, what's the next one? Oh, resonance. And we already got into this a little bit. So let's keep track of them here. And it's resonance of the conjugate base here. we're interested in, right? So let's see. How about this? And how about this? And how about this? These are all OH acids, right? You could say they're all related to alcohols, OH groups. We call this one phenol. That's a functional group where you have an alcohol right on a benzene ring or an aromatic alcohol, phenol. It's in Lysol, the cleaning agent. It's the antiseptic material developed by Joseph Lister about 100 years ago for surgeries. It has antibiotic properties. They'd make an aerosol spray of it and spray it around in the operating room to keep gangrene from growing inside the repaired tissue inside the body. So it's kind of a famous molecule there, phenol it's called. And then we got acetic acid, right? So let's look at the pKa's here. 16. And I remember that one based on water, right? Water is 15.7. And alcohols are indeed water-like, if that's all they are. No other factors involved, right? They'll be around 16. What about phenol? Oh, we already have carboxylic acid, 5. I drew phenol right in the middle. So you already know that that's probably where its pKa is going to be. But we need to figure out why. Indeed, it turns out to be 10. The same as that diketone, which is kind of a good thing to know. If you want to start memorizing a big list, that would be another one to put away. But structurally, let's see if we can figure out why is it what? More acidic than a typical alcohol. And why is the carboxylic acid the most acidic OH group here? Okay, let's see. Well, I'm already giving it away, resonance. Let's look at the conjugate base. There it is. If we take the proton off, we just get ethoxide. Okay, can we resonate that anywhere? No, we have 2 hydrogens here. That's tetrahedral. We have the 3 lone pairs, and that's kind of the end of the road. That's all it can do. It's on an electronegative atom, and that's why it's somewhat acidic to begin with, right? 16. If this was a carbon, that would be up around 50. And so the electronegativity, all these factors kind of go together, right? So focusing on structure will help you remember these ideas. So why is phenol more acidic? Well, we got to examine the conjugate base. And what do we see? We see something next door that's different, right? The benzene ring. Okay, can we resonate, delocalize that negative charge, share the joy of the negative charge? Yeah. So let's see. Let's resonate here. Draw the resonance structure. It'll look like what? We're just moving electrons, right? That becomes a ketone, and this becomes an anion, right? There's still a hydrogen there, but those are indeed resonance structures, right? Is there another one? In fact, there's 2 more, right? Where else can we draw this? Yeah. Keep on going. Yeah. So let's see. Is that another one? Yeah, then we'd have the negative charge out here. And there's another one still, right here. And then that one is degenerate with this one. There's some symmetry there. But let's see, the negative charge is shared over 1, 2, 3, 4 atoms. If you smear out that negative charge, that tends to stabilize that molecule, okay? Which means what? It weakens this bond to begin with and allows this to react more vigorously, okay? Be a better proton donor, okay? So there's a couple factors there. 4 resonance structures. What about acetic acid? Well, we've already talked about that. But remind yourself of what? The resonance effect, okay? There's the negative charge on oxygen. Is there a resonance structure here? Yeah, it's this one. They're degenerate. That's okay, the same energy. But the negative charge shared over 2 atoms. It's smeared out, so it's more stable. So wait a minute. What's the issue here? There's 4 resonance structures, and it's only 10. Here there's 2 resonance structures, but this is the more acidic one. Question or explaining this? Explaining it. Very good. What do you think?
Is it due to the induction effect because oxygen is more electronegative?
Yeah, well, I would say it is due to electronegativity because both resonance negative charges are both on electronegative atoms. Oxygen's 3.5 on the Pauling scale. Carbon is 2.4. So even though there's more over here, that's not a stabilizing effect as having both resonance forms on the electronegative one. Does that make sense? Yeah. And someone else probably had the same idea there. Was that the same idea? Okay, very good. Let's compare that to this. Just to be thorough here, sulfuric acid. Now this is inorganic stuff, right? But you know sulfuric acid's a super strong acid. Why? pK of -3. Much more acidic than acetic acid. Well, let's examine the conjugate base. What do we have? So how stable is that? What can you see there? Couple things. What two things can you identify that are going to make that? Electronegativity, right? And sulfur is more electronegative than carbon, so that will enhance that. And plus, what's the other key factor? Resonance. Now, how many resonance structures can you draw? You can draw that one, or you could draw this one, okay? And so you could say it looks like this. Okay, where that negative charge is over 3 different electronegative atoms, okay? So the pKa is lower and the acid is stronger than acetic acid. Is that okay? So these factors are universal that way. Oh, here's one. Let's talk about an explosive compound, picric acid. And it's called an acid. Well, it's got a couple strong reactivity. Its pKa is 0.3. Phenol, the pKa is 10. Picric acid is also a detonation hazard. It's just as explosive as TNT, which is trinitrotoluene. We won't get into that factor. But let's draw out the nitro groups. What do nitro groups look like? Oh, and that's a functional group. Nitro groups coming up in chapter 3. So a nitro, probably seen those before. It's on nitric acid, by the way, which is just protonated nitrate. And there's a charge right there. Overall, NO2 is neutral, but if you draw out the whole Lewis dot structure, it's doubly bonded to this oxygen, so it's plus charge here, singly bonded here, and negative charge there. It itself is resonance stabilized. Let's see why the super low pKa, why the high acidity? Anybody? What factors? Well, let's look at the conjugate base. Take the proton off. Here's what results. We got the same resonance structures, right? Here, 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 or here. But what can we do? Let's draw another one here. Do you see another resonance structure? In fact, you should be able to see many more resonance structures. This is one of the most highly delocalized. In fact, it's a bright yellow compound. You take the proton off, it switches its color, and it's this delocalization of electron. Oh, up to there. See if you can draw that resulting resonance structure with now a negative charge and a double bond right here between carbon and nitrogen, right? In fact, you could push these electrons down here also out onto this nitro, or around over here out onto that nitro, okay? So I think you can see why the pKa drops. And picric acid lives up to its name. It is an acid. It's a pretty strong acid, okay? But yeah, questions on that, picric acid there? That kind of shows you another factor. Let's look at the last factor here. Sorry, we got a few. Hybridization. Hybridization is another important factor. And let's see, you kind of had a feel for it, and we talked about it last time. Let's compare these guys. An alkane, an alkene, an alkyne. Well, you can look off the chart there. We still got it up there. And so what are they? pKa of an alkane is 50. pKa of a alkene, 44. pKa of a terminal acetylene, proton right on the end of a triple bond. Now, all of these result in what? A pair of electrons left behind on carbon, okay? From the alkane, this generates what? An sp what? What's the hybridization of this carbon still? sp3. Very good. So all four of those atomic orbitals are mixed, right? The 2s and then the 2p's. All mixed together, create the 4 equivalent sp3 orbitals that point at the corners of the regular tetrahedron, okay? This one's a little bit different. What's that? It came from an alkene, so that's indeed what hybridization? sp2. One of the p's is still in a double bond here, perpendicular to this system. We can't actually resonate there because this anion that results is perpendicular. There's a node right at the carbon. That does not communicate electronically with that alkene, okay? And how about this one? Well, that's indeed sp. So hence the stabilization here. What do we say? Percent S here is 25%. And the s orbital character is closer to the nucleus. And the nucleus is positively charged. That's what's going to give us the stabilization here. The proximity of this lone pair in the anion to the positively charged nucleus. So there's 25% S character here, 75% P character. And the P atomic orbitals are bigger. They're out further in space. This one's what, 33% S? So it's held a little bit closer, hence the enhanced acidity. This one here is 50%. And that's the one that gives us this practical acidity. We have a lot of bases. We can easily deprotonate this if we use a strong enough base. Let's see, what would be a strong enough base? How about sodium hydroxide? Will that give us the anion there? Well, it'll give us water. That will be our conjugate acid. But look, its pKa is 16. Is hydroxide a strong enough base to take the proton off of that? No. Do your back of the envelope calculation, right? That would be what, 10 to the minus 9. Can we come up with a stronger base there? We just have to have something that has a conjugate acid that's smaller. How about sodium amide? Yeah, there then we get what, ammonia, NH3 is our conjugate acid, right? And what's the pKa of ammonia? 38. So is sodium amide a strong enough base to take that proton? Yeah, it is. Very good. Okay. You can smell the ammonia coming off that reaction. And then you can see your sodium acetylide anion, and then we can do reactivity that we'll see later on. All right, so hybridization. Let's do an exercise here, a problem that I consider a harder problem. Complicated molecule. Let's have a carboxylic acid that has an alcohol, that has an amine, that has a sulfide, that has an alkene. So looking at all of those hydrogens as potential acids, let's add a base. Okay? And let's add a super strong base here. And which one will come off first? Let's see. What's the most acidic one here? Well, we already know a couple things on acidity. What's acidic carboxylic acid? pKa of 5. Remember the pKa of an alcohol? 16. pKa of a neutral amine. Let's see, is that 9 or is it 38? Now I'm drawing this as a neutral amine, right? So what number do we use, 38 or 9? What's the one up on the board there? 38. Why didn't I use 9? If this was this, an ammonium cation there, then we would have used what number for pK? Then this would have been 9, okay? So this is a neutral amine, okay? We're talking about loss of that proton to go to amide, N minus. Here we're talking about loss of a proton to go from ammonium to ammonia to the neutral amine. See the difference there? That's a common problem, pitfall for beginning students, not recognizing the difference between an amine acid versus an ammonium cation acid. They're very different things, 38 versus 9. So right here, we're just talking about that. What about a thiol? There's a functional group you're probably not familiar with, but it is on the quiz. So I guess we're going to look at it now. It's 10. It's about the same as phenol, which is kind of a strange one because sulfur is less electronegative than oxygen, but it's a bigger atom. It's further down in the periodic table, and that bigger atom makes this a weaker bond. It's easier to pull off, and it's a sulfide. There are sulfides in amino acids. Maybe you've heard of cysteine before, which forms the disulfide linkages in proteins. So thiols is an important group to know. So we got 10. And then what's this one? This one's on the chart. What's that number for the alkenyl hydrogen? 44. Very good. There you go. Okay. So if we add a base, which proton's going to come off first? Which is the most acidic one? Remember, it's an inverse scale. So which one will come off first? One equivalent of base will make that. Okay. So we'll keep track of our equivalents. You can titrate it in, actually, and see that. So there's our first equivalent coming off there. And what would be our next one to come off? Right here. So if we had 2 equivalents, we'd get that, dianion. 3 equivalents, next one would be here. Okay, 3 equivalents. Well, which one would be next? This one. And we'd have to have a pretty strong base at that point. And by the way, to create polyanions like this is an uphill thing. You'd have to have a super strong base. So this is kind of a theoretical experiment we're doing here. But you get the story. The last one to come off would be this guy, which would be this, right? So, yeah, so those numerical numbers there have an important effect. Let's get to water here. Let's go back to water. And we talked about water to begin with when we talked about the Kas last time. Let's see, when we talk about water, talk about the pH scale, which goes from 0 to 14. And when we talk about water, pH actually equals minus the log of hydronium ion. So you got to remember a little bit of Gen Chem there, acid-base theory. Water can function as an acid or a base. Water can disproportionate equilibrium-wise into hydronium ion plus hydroxide, right? And there's an expression for this called the Kw. Remember what that is? Kw equals the concentration of hydronium ion times the concentration of hydroxide, and it always equals what? It doesn't ionize very much, but it does ionize even under, well, actually under all conditions. There's always some amount of hydronium, some amount of hydroxide. The product is always what? 10 to the minus 14. Very small, but this has important implications. If you have a solution that's pH 0, what does that mean? It means the concentration of hydronium ion is what? Put it in there. pH 0 here. You have to do the inverse log of 0. What is it? It's 1. Okay. Concentration equals 1 molar. And you can get that if you put 1 mole of hydrochloric acid or 1 mole of sulfuric acid in water. It'll completely ionize and make 1 mole of hydronium ion. And if you put your pH meter in there, it will register 0. Okay. pH 1, this is equal to 0.1 molar hydronium ion. pH 7, the hydronium ion is minus 7. Well, maybe we ought to back up here. If your pH 0, hydronium is 1 molar, what's hydroxide at that point? Remember, this is always a constant. So hydroxide at 0 pH is what? 10 to the minus 14. It's still there. And if you're at pH 7, hydronium ions minus 7, and hydroxide's also 10 to the minus 7, okay? And if you're at pH 14, what does that mean? That means hydroxide is what? 1 molar. And hydronium ion is what if you're at pH 14? It's 10 to the minus 14 to get that expression to always be there. Okay, mathematically, I see some eyes glossing over. And wow, that's a lot of math. Is you can expect us to derive all this and do a bunch of calculations? No. What I expect you to know is what this pH scale means and how it relates to organic molecules. So here we got pH. So here's the fourth corollary. 50-50 ionization to protonated for your specific acid we're talking about when the pH is the same as the pKa. Now, what does that mean structurally? That's the important thing. Let's look first at carboxylic acid. It can be protonated, neutral, or it can be deprotonated, acetate, right? At what point is it 50-50 ionized? Well, its pKa is 4.8 or 5. And that's the point on the pH scale. If you have a buffered solution that's about 5 pH, you'll have 50-50, what? Protonated versus deprotonated. Okay, even then, that doesn't make much sense. But let's talk about neutral water. If you put acetic acid into neutral water has a pH of 7. Is that on the basic or the acidic side of the pKa we're talking about? It's on the basic side, right? Remember, this is an inverse scale too. This is super strong acid down here, right? And this is super strong base over here. Okay, and it's that continuous scale. The equilibrium constant for the water ionization is going on there. So if we're over here on the acidic side, it will always look like this. Well, numerically, you can kind of figure it out. If it's 1 pKa unit off, it's 1 part per 100. If it's 2 pKa units off, it's 1 part per 1,000. Okay, and that's okay. But if we're way over here, neutral water, if we put acetic acid into neutral water, what does it end up being? It ends up being acetate, which means what? The water, even though it's neutral, is basic enough to rip that proton off and make acetic acid acetate. Okay, so you just got to keep in mind this is the basic side. Okay, this is the acidic side. Okay, and then where is your pKa? And then ask yourself, are we on the acidic side or the basic side of that pKa? And then you'll always know what the ionization state of your molecule is going to be. Okay, very important for amino acids coming up. So let's see, what's the other one we need to talk about? Oh, how about this? Methylamine versus methyl ammonium. Let's put an amine in solution. Let's put it first in solution here where it's at 7. Now, what's the pKa of ammonium cation? Now, that's one I wanted you to know, right? And it's not on the chart. What is it? That's the one that's 9, right? And so if we're at pH 7, is that the acidic or the basic side of its pKa? To the left is acidic, right? That's your left, my right. Okay, so what is it? If we're on this side of its pKa, we're on the acidic side, and so there's enough protons around to keep that protonated, and it's going to have a charge of +1. Okay, acetate here has a charge of -1 at that pH. Okay, so you got to keep these straight. Ionizing in this case goes from +1 charge to what? To neutral. But if we're over here, let's say at 12, pH 12, whatever, if we put an amine in there, will it be ammonium protonated or will it be neutral amine? We're on what? The basic side of that pKa. So will it be neutral or protonated? Okay, I'm giving you this to make it simpler. I could make you use the Henderson-Hasselbalch equation to figure this out. Which would you rather do? Qualitatively or mathematically? I don't know. Structurally, though, you should see. If this pK is 9, this relates to the pH scale. If we're on the basic side of this pKa, we're increasing hydroxide over here to the right, correct? That means we're going to have more of this. Okay. In fact, at pH 12, it's all neutral amine. If we're anything lower than 9 down here, we're going to keep that guy protonated. Okay. So this lets you figure this out. This has to be in water. This is a pH scale 0 to 14. So this doesn't apply to alcohols or alkanes or alkenes or anything with a super high pKa. Okay, because they're always going to be on the acidic side of that and always be protonated. But it's these that have pKa's in this range from 0 to 14 you need to worry about, which are most of the biological molecules. So it's important to keep that straight. Questions on this? We'll just keep it qualitative. We'll review this subject when we get to some other topics coming up later on. But it's important to introduce this idea of ionization state. Yes, please. Right, correct. And I mentioned that with alcohols. Yep, yep, yes.
Just to clarify for myself, so the pKa is 9, so we look at the chart,
Uh-huh.
and then anything higher means that it's deprotonating, but if we go lower, then we know that it's keeping its proton?
Yep, that's all that means. Here we have high protonation strength, right? Way up there, we have low protonation strength. It's just the opposite, acid base. But the pKa numbers can help us out there. All right, let's look at Lewis acid, Lewis bases, just real briefly. A Lewis acid has an empty orbital on it, something like boron trifluoride. And before we talk about protic acids, which have the ability to donate a proton, but they also have an empty, sigma star orbital. So kind of similar this way. But there's a number of compounds that are not Bronsted acids, but they're Lewis acidic if they have an empty orbital. So things like fluoride or hydroxide can react here with these type of things to make these type of products. In fact, tetrafluoroborate is an octet stable compound, okay? Where the initial thing, trifluoroborane, so the 3 valence electrons is not Lewis acidic there. And there are other types of Lewis acid, Lewis base interactions we can talk about here. We can react this with a ketone. So here's our Lewis acid still. Here's our Lewis base, which is a lone pair donor, okay? And if we put that Lewis acid on there, we get this. Now you have to adjust your formal charges there to talk about that. But we can use that to activate this toward nucleophilic attack and make this partially positive, even more reactive there. We can also think about other types of species with Bronsted acids. So here's a typical Bronsted acid, right? HBr, very strong one. And then we have a Lewis, base here. But this isn't a lone pair. These are pi electrons, okay? And we talked about that before. So here's our base. Here's our acid, but we call that a Lewis base because it is a pair of electrons that's donating there. It's accepting a proton. Here it's a Bronsted base, you could say. But it's a similar type of idea there, right? And the resulting thing is that. All right, I've got a demonstration here. Hopefully this shows up okay. We're out of time, darn. So this is universal indicator. You've probably seen this one before. I put CO2, carbon dioxide into water. That creates carbonic acid, okay, which is acidic. And there's 4 indicators in here that change their color based on the pH. So let's see if I can get this to go back. The darker colors are at high pH, high base. This is sodium hydroxide. There it goes back. And then the bubbling overcomes the amount of equivalence I added for the base here. Okay. It should come back. Let's see. Maybe add a little more. Oh, there it's coming. Okay. Oh, there we go. Should go back to yellow. That points out the reversibility. We're changing the pH, okay? Hydroxide, if you dump in enough, that's what, pH 14? Carbonic acid only drops the pH down to about 6. Carbonic acid's pK is about 6. But yeah, that one's there. And then we have sodium polyacrylate salt, which is an ionic polymer, which is a great compound here. And there's just a little bit of polymer here. In fact, I'm going to dump out quite a bit of it. I'm just going to have like a gram in there. I'm going to put in a whole beaker full of water and see what this ionic polymer can do here. Okay, yeah, I didn't even need to stir it or mix it. You see it grabbed onto all that water. In fact, this is called superabsorbent material. It absorbs 10,000 times its weight in water, and it includes that compound and doesn't let the water come out. In fact, you can come up and touch that. It doesn't feel like water at all anymore. It's a gel now, suspended gel. Where do you think you might use this material, superabsorbent? Diapers, very good. I say that this compound, polyacrylate sodium salt, has done more to save marriages than any other compound known. Why? Because guys will change diapers now. Before 40 years ago, guys never got anywhere near a diaper, right? But now the stuff, the material works so much better. No, okay, we're not all wimps, us guys, are we? Okay, very good. So we'll see you on Wednesday, at least through the video. And chapter 3, functional groups. Very good.